3.1 is measures of center. We want a value that measures the center of a data set. In particular, we'll find mean, median, mode, and mid-range. Our objective is not only to find the value of each measure of center, but also to interpret those values. So a measure of center is literally just the value at the center or middle of a data set. And we like finding these. We like finding the mean or arithmetic mean because we know how to do that already. When you find the mean, you add up the numbers and you divide by the number of numbers. We already know this, okay? Add all the data values and divide by the total number of data values. That's mean. That's the same as it's always been. That's one of our measures of center. Important properties of the mean. Sample means drawn from the same population tend to vary less than other measures of center. This is going to be an important word at some point in this chapter, is how much the data values vary. How much are they different from the mean or from some other measure of center. The mean of a data set uses every data value. A disadvantage of the mean is that just one extreme value or outlier can change the value of the mean substantially. And we get this word resistant, or in this case, the mean is not resistant. And that word is going to come back over and over throughout the chapter. So that's not a word that you know, I don't think, resistance. But as soon as you can learn that word, the sooner the better. A statistic is resistant if the presence of extreme values or outliers does not cause it to change very much. So go back and read what this says. All right. The mean is not resistant. And so what that means is one outlier is going to change the value. All right. And an outlier is going to change the value of the mean, not resistant. So we've got some new notation, and I know students always struggle when you get new notation. It's just like vocab. You have to learn the symbols in the same way that you learn vocab. So this is the Greek letter sigma, but anytime you see that sigma, it means the sum. We're adding up a certain set of numbers. And x, that's just going to be our numbers that we're looking at. We're going to have a list of numbers. And so each of those individual numbers is going to be one of the x values. So maybe there's a list of 10 numbers. There's 10 x values. N represents the number of data values in a sample. Capital N represents the number of data values in a population. So remember in a previous chapter, those were two of our terms, sample and population. Population was like everybody, and then sample was just like those that we selected. It's gonna be weird because we're gonna have to think about whether we're talking about a sample or whether we're talking about a population, because this N would be different depending on which one we're talking about. X bar, that's how that's pronounced, is X bar, and that's going to be the mean of sample values, the mean of a set of sample values. And so I know this notation looks difficult, but remember that sigma means sum. And so all that says is we're gonna add up all the values and divide by the number of numbers. So yeah, that's mean. That's the same way that we've always calculated mean. You add up all the numbers and you divide by the number of numbers. That's mean. This is a Greek letter that maybe you've seen before or maybe not, but it's mu. It's the Greek letter mu, and this is the mean of the values in a population. But the formula is still pretty much the same thing. Sigma means sum. So we're going to add up all the numbers and divide by the number of numbers. Remember the difference between little n and big N. Little n's talking about a sample. Big N's talking about a population. So that's really the difference there. You want to learn that. You want to keep that in mind because they've got different symbols and different notations. X tilde is the one that I've seen the least X tilde is the median of a sample. Okay, I kind of prefer writing MED, but that's just me. But X tilde. We don't use the term average, even though that's what the mean is. There are other meanings for the word average. All right, so we don't say average, we say mean. Never use the term average when referring to a measure of center. The word average is often used for the mean, but it is sometimes used for other measures of center, so it's confusing. The term average is not used by statisticians or by the statistics community or professional journals, so just don't use average, use mean. Example 1. We're finding the mean. Find the mean of the first 5 data speeds for Verizon, which are. So you can rely on your prior knowledge here. We're finding the mean. So you add up the numbers and divide by the number of numbers. That's what it is. But the formula, okay, are we talking about a sample or are we talking about a population? Looks like we're talking about a sample, right? So the formula would say X bar equals sigma X over N. And I know that's confusing, but all that means is add up the numbers, divide by the number of numbers. Add them all up, divide by 5. So I'll let you do that on a calculator, but when I add them all up, I get 153.7. And then we're going to divide by 5 because there are 5 numbers. And then we get 30.74. That's the mean. The median of a data set is the measure of center that is the middle value when the original data values are arranged in order of increasing or decreasing magnitude. The median doesn't change by large amounts when we include just a few extreme values, so the median is a resistant measure of center. So, there's that word again, resistant. Remember, the resistant means outliers don't affect the value too much. Okay. The median does not directly use every data value. For example, if the largest value is changed to a much larger value, the median does not change. To find the median, first sort the values or arrange them in order, and then follow one of these 2 procedures. If the number of data values is odd, the median is the number located in the exact middle of the sorted list. If the number of data values is even, the median is found by computing the mean of the 2 middles, the middle of the middle. Okay. And I know you've done this before. I know you've found the median. Median means middle. And so that's what we're trying to find. Find the middle of your list of numbers. So example 2 says find the median of those same numbers. First thing we want to do is put them in order. So we want to line them up in order from smallest to biggest, the way I like to do it. 14.1, 22.4, 23.1, 38.5, 55.6. Put them in order. And then since there's 5 numbers, an odd number, it's just the middle. All we're talking about is the middle number. The median is 23.10. Now that leads me to a weird kind of thing. Somewhere in this chapter, it talks about rounding. And typically what we want to do is we want to keep 1 more decimal place than what they give us. And that seems kind of weird in this problem, but that's why I added a 0 on there. And you'll see it at some point. Can't remember right off the top of my head where I found that. It's coming in a couple of slides. But the median for now, 23.10. That's the middle. Number 3 says repeat the same thing, but now we've got 6 numbers. So again, we want to put them in order. 14.1, 22.4, 23.1, 24.5, 38.5, 55.6. This time there's an even number of numbers. And so if you look at the middle, 1, 2, 3, 1, 2, 3, the middle is right there. And so we just need to find the middle of a middle, or the mean of these two numbers. So we're going to take 23.1 plus 24.5 and divide by 2. We get 23.80. That's the median. The mode is the data of a data set is the value or values occurring with the greatest frequency. Most. Mode. Most. The one that occurs most often. That's the mode. The mode can be found with qualitative data. Remember, qualitative, it's talking about numbers. Actually, no, I said that wrong. Quantitative. Quantitative, quantity, that's talking about numbers. So this is non-numbers, all right? Words, because all you have to do is just see which word or which whatever it is, which category, which whatever it is happens the most frequently. And they don't have to be numbers in order to find the one that happens most often. So qualitative is talking about non-numbers. A data set can have no mode or one mode or multiple modes. And that's the only time I think it gets confusing is when you've got like 3 modes or something. When 2 data values occur with the same greatest frequency, each one is a mode, and the data set is said to be bimodal. Well, bi means 2, so if there's 2 of them. When more than 2 data values occur with the same greatest frequency, each is a mode, and the data set is said to be multimodal. So anything that's greater than 2, I guess, right? Multimodal. When no data value is repeated, we say there is no mode. So if each number only happens once, and every number only happens once, we're going to say no mode. So probably the easiest one to calculate, assuming you have those little stipulations in check. Find the mode. Well, I see 1, 2, 3. I see 0.3 happens 3 times. That's the mode. And in part B, I see 0.3 happens a couple of times and 4.0 happens a couple of times. This one's bimodal. So that mode is 0.3 and another one at 4.0. The next one, none of the numbers repeat. None of them repeat. So we're going to say this one has no mode. No mode. Now, mid-range is probably the only one of these terms that you've never done before. It's not hard, but you might not have done this one. The mid-range of a data set is the measure of center, that is the value midway between the maximum and minimum values. It's found by adding the max data value to the minimum data value and dividing by 2. So here's the formula. You're going to take the max plus the min divided by 2. Because the mid-range uses only the maximum and minimum values, it is very sensitive to those extremes. So the mid-range is not resistant. Okay, there's that word again. Again, resistant means that outliers don't change the value much. So this one is not resistance. Outliers do change the value quite a bit. Important properties. In practice, the mid-range is rarely used, but it has 3 redeeming features. Number 1, it's easy to compute. Number 2, the mid-range helps reinforce the very important point that there are several different ways to define the center of data. And 3, the value of the mid-range is sometimes used incorrectly for the median, so confusion can be reduced by clearly defining the mid-range along with the median. Example 5, find the mid-range. So mid-range, remember what we do? We take the max plus the min, divide by 2. 55.6 plus 14.1 divided by 2. Going to get 34.85. Well, here's where it's going to say that, okay? For the mean, median, and mid-range, carry one more decimal place than is present in the original set of values. So there's only one decimal place, so I kept 2. All right. And we can verify this, I guess. 55.6 plus 14.1 divided by 2, 34.85. If they give you one decimal, keep 2. That's what this round off rule says. Round off rules. For the mode, leave the value as is without rounding, and this is because values of the mode are the same as some of the original data values. We're not even really doing math with the mode, okay, for the most part. Critical thinking. We can always calculate measures of center from a sample of numbers, but we should always think about whether it makes sense to do that. We should also think about the sampling method used to collect the data. Sometimes mean, median, and median are not meaningful statistics. Part A, there it says zip codes, and they list off some zip codes. It wouldn't make any sense to find the mean of those zip codes. You add up all those numbers, you divide by 5. That doesn't mean anything, okay? That doesn't tell us anything. So sometimes it's not meaningful. Ranks of selected national universities, 2, 3, 7, 10. Again, if we found the average of those 5 numbers, the mean of those 5 numbers, it doesn't really tell us anything. I saw another example where they were talking about like the jersey numbers on a football team. And even though we could find the mean of those jersey numbers, it doesn't tell us anything, so who cares? That's what they're saying. All right, now this is probably the hardest thing that we've done so far, finding the mean from a frequency distribution. Remember, we had this example in chapter 2, I believe. It was talking about serving times at McDonald's. But if you've got a list of numbers, what this means is there's 11 numbers in between that range right there. All right, I don't know what they are, but there are 11 numbers between 75 and 124. So we look at this equation for finding the mean from a frequency distribution, and that's difficult. I see that sigma a couple of times. Sigma means sum, but it says first multiply each frequency and class midpoint. So there's the key right there, is you're going to have to find the midpoint for each of the rows, for each of the classes or categories, then add those products. So that's what the top line says. Then we're going to have to divide by the total number in the frequency table, the total number of numbers. I think the best way is to look at an example. So when we see this frequency distribution, we need to find the midpoints of each of these classes. So the midpoint of 75 through 124 is 99.5. That's the midpoint. Add the 2 numbers and divide by 2. Add them and divide by 2. The midpoint of this is 149.5. Again, if you don't understand what I'm doing, I'm just saying 125 plus 174 divided by 2. 149.5. The midpoint of this is 199.5. The midpoint of this is 249.5, and this midpoint is 299.5. So we want to find those midpoints, the middle of each of those ranges. And if you look back at the formula, it says we're going to multiply each frequency and class midpoint. So I want to take 99.5 times 11. And that gives me 1094.5. And I want to take 149.5 times 24. That's the frequency. There are 24 numbers in that range. So 149.5 times 24 is 3,588. Check me on a calculator if you like. 199.5 times 10 is 1,995. 249.5 times 3 is 748.5. 299.5 times 2 is 599. At the end of the day, we're just finding the mean, and so it would make sense to add them all up and divide by the number of numbers. That's the definition of mean, right? Add them all up and divide by the number of numbers. And so that's exactly what we're going to do. We're going to take the sum of those 5 things. 1094.5 plus 3588 plus 1995 plus 748.5 plus 599 gives me 8,025. The sum of those 5 numbers is 8,025. And so our mean, x bar, equals that sum divided by the number of numbers. Okay, now be careful because we're talking about the frequency numbers. There were 11 numbers and then 24 more numbers and 10 more and 3 more and 2 more. You may remember those numbers add up to 50. So we're dividing by 50 because that's the number of numbers in that data set. 8,025 divided by 50. $160.5. Let's call that 160.50. There we go. Okay. Weighted mean. When different x data values are assigned to different weights, we can compute a weighted mean. Something similar is how your GPA is calculated. You've got different grade weights, different classes, different grades. And so this is the sum of the weights times each x number, divided by the sum of the weights. I think it's probably easier just to get in and do an example. So weighted mean. Computing grade point average. In her first semester of college, a student took 5 courses. Her final grades, along with a number of credits for each course, were A at 3 credits, A at 4 credits, B 3 credits, C was 3 credits, F 1 credit. So we want to compute the grade point average, knowing that A is 4 points, B is 3 points, C is 2 points, D is 1 point, and F is 0 points. So I think it makes a lot of sense. If you look at this first one is an A and 3 credits. So we know A is 4 points. So it's 4 points times your 3 credits. And then we've got another A, but this time it's 4 credits. So we're going to add the 4 credits times the 4 points for an A. And then we've got a B at 3 credits. So that's going to be 3 points times 3 credits. We've got a C with 3 credits. So a C is 2 points, so we've got 2 times 3, or 3 times 2. It doesn't really matter. I think I got switched there. 3 credits worth 2 points each. And then we've got 1 credit of F. So F is 0 and times the 1 credit right there. That's going to be your numerator. The sum of the products. And then we need to divide by the sum of all of those weights, okay? Or the credits, okay? There were 3 credits plus 4 credits plus 3 credits plus 3 credits plus 1 credit. That's what we're dividing by. And so if we look at that numerator, the numerator, we're going to have 4 times 3 is 12, plus 4 times 4 is 16, plus 3 times 3 is 9, plus 2 times 3 is 6, plus 0 times 1. And on the bottom, 3 plus 4 plus 3 plus 3 plus 1, that's 14. So cleaning all of that up, 12 plus 16 plus 9 plus 6 plus 0 is 43. We have 43 over 14. It's about 3.07. 3.07, that would be her GPA.